This finally is section 1-9. Okay. Essentially, it's a summary and a bit of extension on the earlier sections. The kind of reasoning we've been talking about is called deductive reasoning. It's got stricter standards of validity than the standards applied in daily pursuits, right? Day-to-day stuff. But you probably know that because there are times when things that you say that seem perfectly reasonable somehow in a math class don't go over as well. That would be deductive reasoning. But there's something else called inductive reasoning. And that's when you make a generalization based on the evidence of a whole lot of examples. And you'll notice in the last section, we referred to improper induction. Right? And we said that was where there just weren't enough examples, or we hadn't tied the examples together in a way that proved what we were trying to say. That made it an invalid argument. And of course, what I said before was even if there are an infinite number of examples, like for the prime numbers being odd, that's not enough. Okay. There is a method of induction that you can use, but I don't think we're going to go over it at this point. Right? Albert Einstein, no amount of experimentation can ever prove me right, but a single experiment can prove me wrong. So for science and for most of people in the real world, after a while, you start to say, you know, I kind of think that we've had enough examples of this, that it's so likely that this is true that I'm just going to assume that it is true. And I'm going to say that we proved it. For example, gravity. Well, how do I know gravity works? How do I know there is gravity? It's because every time I let something go, it falls. Well, does that mean it can't possibly be that I would let something go and it would just hang there? I'm assuming that I'm not in a space capsule or something. Yeah, in the real world, that we pretty much accept that as proof. In the mathematical world, we would not. And there's also diagnostic reasoning. Doctors use that all the time. They refer to it as a differential diagnosis. Basically, what they do, they look at symptoms and start ruling out what the disease might be. So that kind of diagnostic reasoning, or using a differential diagnosis, is not really valid in mathematics. But of course, when you're dealing with a doctor, it usually works. This is also diagnostic reasoning. This is the kind of thing where you check for, if this is true, try this. So this is sort of a formula that you can use to try to troubleshoot. It's another kind of reasoning. And again, it's diagnostic reasoning. And then concluding the inverse of an if-then statement is inverse error when you do it in mathematics, but in everyday occurrences when you're sort of expected to reason this way. If you want to go with us, be at my house at 6 p.m. If you don't want to go, you should not be at the house at 6 p.m. When a person says if it rains, then we're not going to have a picnic, the inference is that if it doesn't rain, there will be a picnic. This part right here is the stuff I started with. If mom says, if you don't clean your room, then you can't go out, there is a reasonable inference that if I do clean my room, I can go out. That's an inverse error, but in day-to-day life, that's how we talk. And you've got statistics, probabilistic reasoning. When you talk about something that has a 99.99997 probability of being true, which is frequently the kind of probability you get when you do DNA matches, those are different kinds of arguments, different kinds of reasoning that we use in day-to-day life that wouldn't work for mathematics, but they work to get us through the day. The difference between inductive and deductive reasoning: inductive reasoning is based on examples, and deductive reasoning is based simply on logical statements. Complete the following diagnostic statement. If TV programs can't be recorded, TV programs can't be recorded, then the connections of the VCR external antenna might not be correctly done. The receiving channel of the VCR might not be properly tuned, or the erasure prevention tab of the cassette tape is still intact. I had promised you that I would show you, as we went through, things about the book that made it obvious that it was an old book. This would be one of them. The idea that we're doing troubleshooting on a VCR. There was another one, actually. The idea that Mr. Mailer is trying to find combinations of 3 and 5 cent stamps that would add up to the postage required. It's been a really long time since any letter required 8 cents of postage. It costs, I think, 55 cents now to mail a letter. And I had a few of you asking me what postage was when we were doing this in the test. So the idea that we have these 3 cent and 5 cent stamps down here, that's an indication that this is an old book. But that's okay, because the math hasn't really changed. Anyway, that's what we just did here. What is the malfunction caused by too much condensation on the unit, indicated by the dew light? Well, let's see. Check the dew indicator. If it's displayed, refer to page 9. If the dew light is on, the operation won't start when the operation buttons are pushed, or at least they might not. So that's the malfunction caused by that. Is too much dew the only possible cause for this symptom? Oh no. Could just be that you forgot to turn the power on. Or it could be that the timer button didn't go on. Okay. What would you check first if timer recording cannot be performed? Timer recording can't be performed. Check the timer setting. That would be the first thing to do. And is this the only possible diagnosis? No. Make sure that the timer button is on. And then it says, list others, including some of the ones not listed on the table. Timer recording can't be performed. Well, there could be a whole bunch of things, right? I mean, it's like maybe it's not plugged in, or maybe it's broken in some other way. I'm going to leave that out because I don't think any of you have VCRs anyway. An example of the kind of diagnostic reasoning you might encounter at an auto repair shop. That's another indication that it's an old book, because for most cars now, you just plug the car into a computer and the computer tells you what's wrong with it. But there was a time when mechanics had to listen and look and figure out what was going wrong with a car and then try to figure out what might cause it. I have a car at the moment where the battery doesn't hold a charge. And there are 2 possible explanations that I know about. A qualified mechanic might know of more. One would be that the battery is old and just doesn't work anymore. And the other would be that the device that charges the battery from the motion of the engine is no longer working. That's called an alternator. So there are 2 possible answers right there, and that's the kind of thing that would be diagnostic reasoning. Give an example of an if-then statement that is intended to be an if and only if statement, different from any mentioned in this lesson. Well, this is like the second paragraph on page 66, where we're talking about things that you can draw an inference from. So, for example, let's see. Well, we can go to the children's song, "If You're Happy and You Know It, Clap Your Hands." There's nothing in that statement that says you can't clap your hands anyway. But the inference there is, if you're not happy or you don't know that you are happy, don't clap your hands, right? That would be sort of the if and only if. Clap your hands if and only if you're happy and you know it. But that's not really what it says. There's nothing in if you're happy and you know it, clap your hands. There's nothing in that statement that says don't clap your hands if you're not happy or you don't know it.
If you're happy and you know it, then your face will surely show it. If you're happy and you know it, clap your hands.
So that would be an example for number 6. Use inductive reasoning based on the information in this lesson to give the probability of obtaining n heads in n tosses of a fair coin. For each time you toss the coin, you multiply again by 1/2. If you toss a coin once, the probability of getting heads is 1/2. If you toss it again, it's still 1/2. You multiply the two together. If you toss it n times, the probability of getting all heads is 1/2 to the nth power. And now we have a function, p of n is equal to n squared minus n plus 41. Calculate the value at 2, 3, 5, and 10. That would be p of 2 would be 43. P of 3 would be 47. P of 5 would be 61. And P of 10 would be 131. Check that all values in A are prime numbers. I think for the moment I'll sort of assume that they are. Would you agree that this is good evidence for the conjecture that for all natural numbers n, P of n is a prime number? Well, no. That would be an example of improper induction. So we're not going to go with that. The conjecture in B is a nice one, but it is not true. Calculate P of n with n equals 41 and show that 41 is a counterexample to the conjecture. We actually don't even need the calculator for this. 41 squared minus 41 plus 41. Well, minus 41 plus 41, those two are going to drop out. 41 squared can't possibly be prime because it's 41 times 41. Assume that a boat loaded with bananas from a South American country arrives at a U.S. port. The public health officers at the port have jurisdiction over the entrance of the produce into the country. They perform quality control by taking a random sample from the load, maybe 100 bananas, and checking them for ripeness and diseases. Their criterion is that if more than 5 bananas in a sample of 100 are substandard, the shipment is rejected. What kind of reasoning are the officers using? They are using induction because they're going by a series of examples. Can they be absolutely sure about the accuracy of their decision? It's an interesting question because there's nothing in the question here, nothing in the problem that talks about accuracy. It simply tells us what the criteria are. Accuracy meaning they were right not to let the bananas into port. If they are using this as a way to indicate that the bananas are all bad, no, obviously not. But how could they decrease the probability of error? Well, if they could check more than 5 bananas, they could decrease the probability of error down to 0 if they looked at absolutely every banana in the shipment. The more bananas they look at, the better the accuracy of their decision. Although, once again, the thing that is missing here is a question of what is it that they are trying to prevent by not letting the bananas in, checking for ripeness and diseases. It's not a question I would give you.
We have no bananas. We have no bananas today.
Let's just sort of flip the page here. Projects. We'll talk about projects in class, but we are going to have projects to do. Summary. This is actually a good thing to know these vocabulary words are things you really should know. You don't need to find the definitions of all of them. The one with asterisks are the ones that you should be able to define. But the rest of them are things you should be able to work with. You should recognize them. And then just so that you know, on the next couple of pages and at the end of every chapter, there is a progress self-test that wouldn't hurt you to look at and see what you can do. There's a chapter review. Okay, so there's a lot of stuff in this book. And then when we get to chapter 2, we're going to analyze some functions. But for now, this is the end of chapter 1.